Hey, it's Adam. Welcome to Nibbles Tutorial Episode 2, where we create the classic snake game with C++ and SFML. In the last episode, we started our project, set up the CMakeLists file, and built the shell of our game engine class. The game currently opens a black window and draws a static snake in the corner. In this episode, we will add movement to our snake and make it respond to keyboard input. We will also add an apple for our snake to eat. If you have any trouble with any of this, or would like to offer support to other people, then please consider joining the community at forums.caf.tech. I look forward to seeing you there. Now, the first thing I want to go over is a slight problem with the input code in the last episode. We're using an event handler to check if a key was pressed. Then we directly poll the keyboard to check if the escape key is currently being pressed. We should actually be checking the event itself. This can in some cases lead to a missed input. Directly reading inputs is useful for games where you want to be able to hold a key to keep moving in the same direction. But in this case, we want to use events instead. So let's fix that right now. In input.cpp, we have our event loop, and we have the keyboard event where it checks if a key has been pressed. And then here we have keyboard is key pressed. This is directly checking the keyboard rather than the event. So we should change this line to say event.key.code is equal to keyboard escape. Now when it gets the key pressed event, it'll check the actual event code and then do what it needs to. So if we test it now, run it, and there's our snake doing nothing. If I press escape, it should work. There you go, fixed. Now let's look at giving the snake some movement and setting its direction. Over in engine.hpp, we should set the snake direction. The snake speed, and time since last move, because we only want the snake to move in steps, otherwise it'll move constantly. So that gives us a direction for the snake to head, gives it a speed, and the time that has elapsed since the last time the snake has moved. Now we'll also need an input queue. We can either read the inputs as they come in, but as the snake only moves in certain steps, it starts off pretty slow and the inputs might not work as you expected. So if we create a queue, you can press as many inputs as you like. It'll queue them all up and it'll read them one by one as the snake moves. To do that, we can't really use a vector, because a queue, we need to be able to add things on the end of the queue and then take them from the front of the queue. Vector doesn't allow us to take something from the front of the queue easily without doing a lot of messy rearranging. But there's another type called deck. It looks like DQ, but it's pronounced deck. It's basically a vector, but it allows popping things off the front as well as the end. So we can easily just take something off the front, use it, and throw it away. And for our direction queue, set a deck of int. Our directions are our integers. Direction queue. There we go. Now, for our actual directions, we could just remember what all the integers are for all the different directions, or we can create an enumerator called direction and use some handy labels. Oops, don't forget that comma there. So now, when we set a direction, we can go direction up, direction right, direction down, or direction left. It's a lot easier than 0, 1, 2, and 3. Now we want to add a direction. We need a function to add a direction. Takes in the new direction. We also want to set up our update function. Our snake can't move without an update function. Now over on engine.cpp, let's set our speed. We'll start out at 2, which will be fairly slow, but as we eat apples, we'll get our speed to increase. Let's set snake direction. This will be the initial snake direction. Equals direction right. Because we already made our snake facing right. The head of it is there, and then the tail of it goes off to the left. And let's set our time since last move. We'll zero that out. Now down in our run function, we're going to need a clock to keep track of everything. There's our clock. It's outside of our main loop, but we'll use that to get the delta time between frames. Because our computer may run fast or slow, if we get the time between this frame and the last frame, then we can do exact timing with events and moving our snake. And to make that work, inside of our game loop, we need to get the delta time. We'll call it dt equals clock.restart. That restarts the clock and returns the amount of time that was spent while the clock was running. And while we're in here, we'll go time since last move plus equals dt. So that adds the delta time onto the time since the last move. So as it loops through, it will keep adding the delta time to this until it gets far enough along, and then the snake will know that it needs to move. We'll also need to run this update function that we haven't written yet. We'll just plonk it in here, ready to roll. Now let's look at our input.cpp again. We'll add some directions. Now we're going to need events for each of the key directions. We also need to make sure that we don't add the same direction twice. So if you press right, you don't want the same direction twice because the second one won't do anything. We also want to make sure that we don't double back onto ourselves. So if the snake is already going right, we don't want him to go left, crash straight into himself. That'd be silly. So to handle all of that, let's create a function. Let's use our add direction function. We're putting this in our input.cpp. We're going to go if direction queue dot empty. So it checks if the direction queue is empty. It'll just put the new direction straight in there. Direction queue dot and place back new direction. Else, if it's not empty, it will check the last element in the queue. So the last key that you pressed, make sure it's not equal new direction. So if the new key you pressed is not the same as the last one in the queue, then we'll add it. Place back, new direction. The reason we're putting this into a function down here is so we don't have to repeat all of this for every key event. We want to repeat ourselves as little as possible. Now up here, inside of our key pressed events, under our quit event, put our direction events. So if event.key.code equals keyboard up, then add direction up. And the next line will be else if event.key.code is equal to keyboard down. Doesn't really matter which order you put them in, just as long as the actual function here matches. So if you're checking for down, make sure you're setting it down. Speed things up, we can just copy that whole block, paste it in another 2 times. So we've got up, down. Let's check left. Make sure it sets it left. And right. Now there might be a cooler, shorter way to achieve this, but I find this a lot more readable. It's easy to understand when you look at it. Now let's create our update.cpp. Remember we created our update declaration in our header. Let's create the source file for that. We'll put it in a separate source file, update.cpp. This file will actually do a fair bit. First thing it needs to do is include our engine header. Now the first thing we'll do in update is update the snake positions. Because our snake is made up of sections, each section needs to move individually and follow each other. But we don't want to do this every single frame. We want the snake to be kind of slow and be able to speed up using that speed integer we declared earlier. So we'll do an if time since last move as seconds is greater than or equal to seconds 1 divided by float speed. We're casting speed into a floating point number. Dot as seconds. We need variables to hold the current snake's position, the current snake section's position as we loop through it, and the last section position, so the previous section. And positions need a vector 2f. This section position equals snake. 0 is always the head. We haven't started our loop yet, so we'll just initialize the snake section position, this section position as the position of the head. And last section position, we'll just set it to the same, this section position. So they're ready to use now. Is there anything in the input queue? So does the snake need to change direction? If not direction queue.empty, so if direction queue.empty, the exclamation mark reverses it. So if not direction Q empty, if it's not empty, let's change direction. This is where we actually make sure we don't reverse direction. We use a switch statement for this. We could use a if-else. A big lot of if-else statements. Let's use a switch. So if snake direction is up, so if it's currently going up, if direction Q dot front, this is the item at the start of the queue, is not equal to direction down, so the opposite of the current direction, snake direction equals direction Q dot front, so the item at the front of the queue, and we put a break at the end of each case. Sorry, we put that outside of that if break. And we put our next case. We can copy and paste these. Again, there may be a cooler way to do this using binary math. I find this easy to understand when you look at it. So up, down, left, right. Now let's fix them up. So down, the opposite of down is up. Left. Oops, we need the opposite. Right. Left. Alright, so if the snake's currently pointing right, make sure the next direction is not left. If it's not left, then we set the new direction. And then after this whole switch statement, we're going to remove the item off the front of the queue. We've either used it or discarded it. We need to break it off the queue now. Direction Q dot pop front. That's what the deck allows us to do, pop front. You can't do that with a vector. You can only pop from the end. Now, because this is going to be a big if statement, I like to just put a comment right on the end of it. Just to show where the end of it is. So if I want to put something down, if I want to keep adding things into it, I know I need to go above that. If I want to add something after it, I need to go below it. So the last thing we actually want to do in here, reset the last move timer. So time since last move equals time 0. Set it back to 0. We will leave this at the bottom of this update snake positions if statement, and we'll add some more stuff above that. We need to update the actual positions of the snake sections. So first we'll update the head position. Update the snake's head position, and then after that we'll update, update the tail positions. So to do the head position, we'll use a switch, snake direction, case direction right, snake 0, which is always the head, set position. We need a vector 2f for the position, and we're going to use this section position.x plus 20. Using a magic number here again, because we know the snake sections are 20 pixels wide. this section position dot y. The y position won't change. The x position will. And then break. We can repeat this for each direction and just change these bits here. So right, down, left, up, down. So if we're going down, the x position doesn't need to change, but the y position needs to increase by 20 pixels. If we're going left, the x position needs to decrease by 20 pixels and the y position needs to stay the same. If we're going up, the x position stays the same and the y position decreases by 20 pixels. Alright, so the head should move. Let's update the tail sections. We can use a loop for that. So for int s equals 1, s is less than snake dot size s plus plus. This section position equals snake. We'll use s as the index. Get position. Snake s dot set position. Last section position. And then we'll update the last section position after we've done the move to this section position. So the very first time around, the last section position will be the original position of the head. So the section directly behind the head will move into where the head was, and then we'll update the last section position, ready for the next section to move into its place. And that's all we need to do to change the tail positions. There's one more bit we need to do. We need to run the update function on the snake sections themselves, so they actually change their sprite's location. Let's change that to run. And we'll use range loop for this one. s.update. Bam. Now at this point, we should be able to test our game, and our snake should move and respond to direction inputs. Let's try it. Oh, there's a little problem. You might notice the snake started here and then it shifted straight up there straight away. But it is moving and responding to directions. Let's try the input queue. That's good. Now let's fix that little bug where he moves at the start. If we look in snake section.cpp and in the constructor, we don't actually set the position to the start position. So the sprite knows where it is, but the actual position variable doesn't. So position equals start position. And that should solve that problem straight away. Try again. Snake starts in the right spot and still works. There's not much for him to do right now, and he will actually go off the screen if you let him. And come back on. Once we add our game level, we can stop that from happening. Let's add an apple for our snake to eat. We'll create a new class for apples. Now you might think when we eat an apple we should destroy it and create a new one, but we don't actually need to do that. We can increment our score and increment everything that needs to be changed and just move the apple to the player. It'll look like it's a new apple. So we'll only ever need one apple. Let's create a class for it. Call it apple. Move our source file into the source directory. Right, so the apple class will be very similar to the snake section class. It'll use a rectangle shape, which requires SFML graphics using namespace SF. Private. Rectangle shape. We'll just call the apple shape a sprite. No, it's not actually a sprite, but we'll call it that. There's our constructor. Now, set position. Oh, we don't need to track where the apple is. All we need to do is set the actual sprite position, the shape position. So we need a function set position. It'll take a vector2f new position, and we need the rest of our draw function needs to be able to get the sprite. So rectangle shape get sprite, and then over in our apples CPP, do our constructor, which will be the initial setup for our apple. We'll give it a starting position, just a hard set one. Won't matter because we'll actually move it straight away later on once we create our move function. Sprite.set size 2020. Sprite.set fill color. Oops. Let's make our apple red. Red apples taste better. Set position, starting position. All right, so we need our set position function. Sprite.set position, new position. You might have wondered what these X and Y things are. You don't need to type those. I probably should have mentioned that in the first episode. They are just shown by C-line, just to remind you of what should be in those fields. So the size function takes a size, and the vector2f takes an X and Y coordinate. They're just little tips to help you fill these things in properly. So we need the get sprite function. It'll just return sprite. All right, so that is the entirety of our apple class. We'll actually close those. Over in our engine header, we'll include our apple header. And then under our snake stuff, we'll instantiate a new apple. Now, what's going to happen when we eat the apple? We want our snake to grow in length. We want the speed to increase. And ultimately, we want the score to increase. We're not going to look at score in this episode. But to increase the size of our snake, we need another integer. How many sections to add to the snake. So when we eat an apple, we add so many sections to the snake. Might be 3, might be 4, we'll decide later. We'll also start our move apple function. Now in engine.cpp, let's create the move apple function. Put it above run. We like to keep our run function at the bottom. Oops. Move apple. Now to move the apple, we want to choose a random location. We want to make sure we don't put the apple inside of a wall. We're not going to worry about that yet because we don't have walls yet. And we want to make sure we don't put the apple inside of any part of the snake. That would look silly. Find a location to place the apple. Must not be inside the snake or a wall. Now, to work out a random location, we should split the game field into sections that are the size of our apple, and then basically roll a random dice and see what we get. And then test that location against any walls or snake sections. So divide the field into sections the size of the apple. Remove 2 to exclude the exterior walls. We'll have a wall all the way around our field. So we'll exclude that to start with, so the apple just can't go on the very border of our game. Need a vector2f. Apple resolution equals vector2f. Take our resolution dot x, divide it by 20 minus 2. Take our resolution dot y, divide it by 20 minus 2. Remember, our order of operations for math functions are the same in programming as they are in normal math. So it'll do division before it does subtraction. Vector2f, new apple location. Now, because we're going to be checking locations, we'll create a Boolean. Bad location. We'll set it to false. And we'll check our locations. If it turns out that we're in a wall section or we're in a snake section, then we'll set that bad location to true and we'll roll the dice again. So to use a random, there's actually some newer random functions in C++. We're just going to use the old school way, which isn't super random, but most of the time you won't notice the difference. First thing we need to do is seed the random generator. We'll use time, null pointer, which should just get the current time in nanoseconds or whatever it's getting it in. Now we're going to start our loop to check all of the locations to make sure we don't place the apple in a bad spot. We'll do a do while loop. So do while loop will do the functions at least once while bad location. And the reason we do that is we want to run through it once. If bad location gets turned into true, then we want the while statement to roll it again. If it stays as false, then we'll just fall straight through. And that'll be good. Bad location equals false. We'll reset it to false every start of the loop. Generate a random location. So new apple location.x equals, we'll need a float here. Here comes some math. There's a random divided by rand max plus 1 unit divided by integer apple resolution.x times 20. All right, that looks very complicated. You'll notice that these are highlighted. This is basically C line telling us that the rand function is old school and its randomness isn't perfect. But as long as we're happy with it, we're happy with it. Now we're going to need to basically copy that for the y coordinate. And we'll just change the x's to y's on the second one. Now, we're not going to bother checking for walls because we don't have any. We'll check if it's in the snake. We'll use a loop. We'll loop over the snake sections. Now here's a long if statement. If s, this is a snake section, dot get shape, so the rectangle, get global bounds. This is its location in the window. Now, if it intersects a rectangle of floating point numbers, new apple location.x, new apple location.y, 20, 20. That's the width and the height of the rectangle. Everything's 20. So that's a big if statement. Let's, can we shrink this down a little bit? So if s dot shape, get global bounds, dot intersects, shrink it down so it fits on the line better. Then if it does intersect, then bad location equals true, and break the loop, break the this loop here. So as soon as we find a section that is right where our new proposed apple location is, we'll set bad location to true. We'll break out of our snake loop. It'll fall through to the while statement, and bad location will be true, so it'll loop around and try again. It'll roll new dice and check again. We'll do a to do here. To do, and check for apple on wall sections. And then after our loop, we're happy that our new location is good. I need to put a semicolon at the end of that. Don't forget to do that. After that, we'll go apple dot set position, new apple location, semicolon. That's the end of our move apple function for now. We'll come back in an upcoming episode to add the check for wall sections. Now we actually need to call the move apple function so that the apple's not in the same place every time we start the game. So after we create our new snake, let's move apple. And we'll also want to initialize the sections to add equals 0. So we're not adding any sections every frame. Now we need to draw our apple. Let's draw it before the snake. Window.draw. You can probably work out what to put in here by now. Apple.getSprite. Now, if we run our game, we should see an apple on the screen, and it should be in a random location every time we start the game. So let's start it. Okay, I've got an error. Null pointer was not declared in this scope. Did you mean null pointer T? Okay. So engine.cpp, we can actually click here and it takes us to the problem. Null pointer, because I capitalized that P. There we go, it's happy now. I should have noticed that earlier. It was red and there was a red line on here. Anyway, that's part of debugging. You find a bug, you work it out. Here we go, so the next time we run it, it should run fine. There we go, our snake's moving and we have an apple on the screen. Now we haven't done any collision detection yet, so our snake will just roll straight through the apple. But if we run the game again, the apple should be in a different location. There it is. Different location each time. Nice. Random. The last step for this episode will be to let our snake eat the apple. He can move around, he can see the apple, but he can't eat it. So in our update function, underneath where we move our snake and update it, we'll do some collision detections to see if it's hit the apple. Collision detection on the apple. In the next episode, we'll also do collision detection for walls. So our snake won't be able to hit walls. Right, so if snake, we're only interested in the head of the snake. Get shape, get global bounds, dot intersects, apple dot get sprite dot get global bounds. So if the head of the snake, its position intersects the position of the apple, we hit the apple. Add more sections to the snake. Increase speed and move the apple. We'll actually put a to-do here. Increment score. Apples eaten. Add snake sections. We're actually going to do that. So increment score, apples eaten, and check if it's time for the next level. There's a little bit of a spoiler as to what's coming up. But for this episode, we go sections to add, plus equals, let's add 4 sections to the snake after he's eaten an apple. Speed plus plus, we'll increase it by 1. And we'll run move apple. Now we actually need to grow the snake. We need to check the sections to add and add sections to it. Well, let's do that up before we move the snake. So before we update the snake's head position, do we need to grow the snake? So if sections to add, so sections to add, so this is just checking if this variable is true. In a lot of languages, anything other than 0 or anything other than a negative value or 0 is true. So if there are sections to add, if it's 1, 2, 3, 4, then this will be true. If it's 0, then it'll be false. It'll skip past it. It's called a truthy. We'll run add snakes section, and then we'll go sections to add minus minus. We'll add 1 section per snake update interval until there's no more to add. Now at this point we should be able to test our game again and eat some apples, see if the apple moves, and see if the snake grows and increases speed. Alrighty, there's our apple. Let's go and eat it. Bam, apple moved, snake grew and got faster. Look at that. Now I'll just show you we're not checking for collisions with his own body, so he can go through himself at the moment. He can still go off the screen, but he's nomming on those apples. Alrighty, we are beginning to get something playable now. Our snake moves around and we can eat apples. It gets longer and speeds up as it eats. Next time we'll add collision detection for the snake hitting itself. We'll also create some walls and learn how to load a level in from external files. If you're getting stuck on something in this episode, then please leave a comment below this video, or even better, come and join our community at forums.caf.tech. Please consider hitting that subscribe button, and if you can, I would really appreciate your support on Patreon or Ko-fi. Thanks for watching. Stay caffeinated.